Good morning, everyone. We are presenting before you the paper with the paper ID 169, and the paper title is Performance Analysis and Control of Bidirectional Converter-Inverter Interfaced Battery System for Electric Transportation. In the recent years, the world has been moving more towards environment-friendly means of energy. The increase in global warming has become a matter of concern, and one of the major contributors to this is the extensive use of crude oils, which increases the carbon emissions. One of the major contributors of these carbon emissions constitutes of the fossil fuel powered vehicles. But nowadays, the batteries or the electric vehicles have been replacing the fossil fuel vehicles for electric vehicle transportation. Electric vehicles are powered using different type of batteries. One of them also constitutes the lead acid batteries, which are one of the cheap yet efficient sources for small electric vehicle applications. In this, DC-DC bidirectional converter can be used to enable power flow in either direction and also for the regenerative braking. And the inverters can be used to supply motor loads from batteries while controlling the output voltage. Limitations of the existing include the excessive use of fossil fuels have become a matter of concern for the environment. One of the main problems with the electric vehicle setups is the control of output power fluctuations. A more optimized and tight regulation of DC link voltage is required for that. Also, we require proper synchronization for the load grid interconnections, which we would be supplying to the motor through the inverter for better control of the vehicle. The contributions of this paper includes the gain of the bidirectional converter is not constant. It varies with the variation in the load resistance. Also, a PI-based vector control technique is proposed for the control of the single-phase inverter, and design of PLL for smooth interfacing with the grid has been used. In the PLL, the output voltage is transformed into its alpha and beta components using a phase shifter of 90 degree, and then it is again transformed into DQ components, providing desirable results over its entire range of operation. Moving on to the system description, the system comprises of a pack of lead-acid batteries, a DC-DC bidirectional converter, and a single-phase inverter with LC filter as shown in the figure 1. The inverter requires a stable voltage input of higher value as compared to that delivered solely by the battery. So the DC-DC bidirectional converter boosts the voltage of the battery from its actual voltage to a higher voltage level. The boosted voltage of the bidirectional converter is then fed to the inverter, which in turn converts the DC into an AC signal, desirable for our required load, that is a motor. A PI-based closed-loop controller with vector transformations maintain the frequency and magnitude of the inverter AC output voltage. The regulated AC voltage can be used in many applications such as induction motors, integrated grids, microgrids, etc. As you can see in the figure 1, there are two switches for the DC-DC bidirectional converter side, which has the gate pulse input as S1 and S2, and in the single phase inverter side we have 4 switches, and they have the gate signal input as A, B, C, D. We will be giving the PWM signals to this gate pulse input after the control using the PI controller, and we will be explaining this in the next slide. The figure 2 shows the control strategy for the DC-DC bidirectional converter and inverter along with its respective circuits. We have in here figure 2a shows the converter controller, B is the circuit of DC-DC bidirectional converter, C is the single phase inverter circuit, D inverter controller, and E is the PLL with DQ transformation. In the A we can see that the battery pack supplies the DC voltage is boosted using the bidirectional DC-DC converter, and using a PI controller we are controlling the voltage and the current to generate our PWM. The PWM sends signal to the gate pulses S1 and S2. From the B portion, the DC link voltage we are getting across the DC-DC converter output terminals. The DC link voltage is then fed to the inverter in C. The inverter uses a phase shifter to generate the alpha and beta components, and using DQ transformation and PI controller as shown in the figure, we then convert the alpha beta components into its D and Q components. Next, using a reference signal for the frequency and using the reference frequency as 50 Hz, we get the delta omega t component, the angle delta omega t, which is used by the cos and sine block for generating the Vd star and Vq star. After summing with the error and using a PI controller, we are able to get the V reference, that is the reference voltage for the PWM, to generate the gate signals ABCD. These ABCD are then fed to the switches of the inverter to get our desired output voltage. Moving on to the results for the DC-DC bidirectional converter, it has been seen that the gain also varies with the change in load resistance. As a result, there are variable level of maximum stable voltages for different loads. We also have different values of voltages for lower values of load resistance. The maximum stable voltage produced by various load resistance are plotted in figure 3. Initially, we can see a progressive increase in the voltage from 1 ohm to 6 ohm, corresponding to a value of 266 volt. Further, voltage variations are found to reduce after 7 ohm and remains between 260 volt and 270 volt. In the figure 4, we have taken 64 volt DC from the battery pack as the input voltage. It has been found here that in initial stage of operation, the gain increases along with the increase in the load resistance. However, after 6 ohm, the gain settles from 4.00 to 4.03, and thus the fluctuations reduce. The results for the inverter in isolated mode, we have the reference frequency and the reference peak voltage as 100 pi radian per second and 100 volt respectively. The parameters of PI controllers are tuned. In figure 5, we can see the output voltage of inverter is 70.7 volt, that is 100 volt peak to peak, when the DC link voltage is 150 volt. Similarly, in figure 6 and figure 7, the output voltage of inverter is also 70.7 volt, that is 100 volt peak to peak, while the DC link voltage is 170 volt and 130 volt respectively. This demonstrates that the output voltage of the inverter is equal to the reference input voltage irrespective of the DC link voltage. Hence, the controller is working as per our requirement. Now in figure 8, the waveform of the inverter current is shown. The current of the inverter depends upon the load. Here the current is equal to 1 ampere peak to peak value, as the load resistance is 100 ohm. Next, in the figure 9, we have the waveform of battery voltage, battery current and DC link voltage. The battery voltage is constant and the battery current is positive, because the battery is providing the power to the system as the system is running in isolated mode. The DC link voltage of the system is also shown. The DC link voltage is controlled by the converter controller. While in the figure 10, we see the waveform of battery voltage, battery current and DC link voltage for grid connected mode. In the grid connected mode, the power flows from the inverter side to the battery side, which in turn charges the battery. Therefore, the voltage is increasing with time. The battery current is controlled from the controller and it is equal to 10 ampere, and it is negative because the direction of current is now reversed. Moving on to the conclusions, we see that when load was increased for bidirectional DC-DC converter, the gain starts increasing till it reaches a specific value and eventually saturates after that. The inverter is tested for both isolated as well as grid-connected mode satisfactorily. The overall setup can be implemented for lower-cost electric vehicles running on induction motors. Also, for the control of the inverter, we have implemented the vector control technique, which is often used in three-phase inverter to the single-phase inverter. Accordingly, we get the results which are desirable and satisfactory. And addition of an extra leg to the inverter switches will make the system capable to run a BLDC drive or a PMSM drive electric vehicle too. Overall, in this paper, we have proposed the control strategy for the DC-DC bidirectional converter as well as the single-phase inverter, and we have found satisfactory results using MATLAB simulations. In the further part, we would be implementing this into the hardware, and then we would be integrating it with a motor for practical results and applications. So, lastly, we have the references. Here are some references which we have used in our paper. And thank you so much, everyone.